Okay, so first of all, thanks to the organizer for inviting me to this conference. And as I already said in the title, I'm going to talk about this particular type of Boltzmann machines, which are the product Jacobi-Theta Boltzmann machine with score matching, which is a project that I'm currently working on with also Daniel Kreff, Stefano Carrazza, and Frank Nielsen. So we started this project a few years ago with the idea that we wanted to build a model which was well suited for PDF estimation and PDF sampling. So basically, we wanted to do something for which we are able to do both density estimation, but also sample this model. And also, we wanted to have some different properties for this model. For example, also a built-in PDF normalization. So we would like to have a closed form expression for this model, contrary to other methods such as neural network, where it is impossible to have a nice analytical expression at the end for the model. And we will also want to have something like a very flexible model with a small number of parameters, and this is also not trivial to do. And in order to do this, we starting from the Boltzmann machines. So a very quick recap about the Boltzmann machine. It is a neural network which is divided into two sectors. We have a visible sector node with NV nodes, and also a hidden sector here. And all this node can assume only binary value states, so it can be either 0 or 1. And all these nodes are interconnected with each other through these connection matrices, which are Q, T, and W. And this system can be viewed as a statistical system, and we can find an expression for the energy. So we'll have these two connected terms, then two linear terms, and finally this coupling term, if you will, between the hidden sector and the visible sector. So keeping this statistical mechanical approach, we are also able to calculate the canonical participant function just by summing this exponential of minus the energy over h and v. And we can find a generic probability of finding a state of finding a state VH with the classical Boltzmann distribution, which is e to the minus EVH over Z. And if we are only interested instead in finding the probability of having a specific state V, we can simply marginalize the variable H. So we can sum over the hidden nodes H, and we get a final expression of this form where FV is the free energy of the system. So as I show you, the expression for PV is a parametric density probability, which depend on the value of the connection matrices, so Q, T, W, and the biases BV and BH. And theoretically, one could imagine that we can start doing some density estimation using the standard Boltzmann machine. However, as I'm sure that some of you already know, this is practically not feasible, and that's why we can recur to other techniques such as the restricted Boltzmann machine. But we still like the idea of the Boltzmann machine, so we wanted to answer a question, which is how can we change the standard approach of the Boltzmann machine in order to perform density estimation. And after a few tries, we discovered something very interesting, so that if we change the domain of the hidden nodes and of the visible node from just being 0 or 1 to some continuous or discrete space. So in particular, if you let V be a real real vector and h an integer vector, if we assume some mild constraint on the connection matrices, we are actually able to compute this probability PV in this nice way, which is a completely analytical expression where we have this damping exponential factor here, and then we have this ratio of this particular function, which are known in mathematics as the Riemann theta functions, and that's why we decided to call this particular model the Riemann theta Boltzmann machine. And here I show a few plots where we can see how by varying the value of the different connection matrices and the biases, we are able to picture with some different cases for how a possible probability distribution could look like. And in particular, let's see that at infinity, everything is going to 0 because we have this damping exponential factor here. And so now I will briefly talk about some properties of this Riemann theta Boltzmann machine. As I've already said at the beginning, our aim is to build a model to perform density estimation. So to perform density estimation, we are looking to solve this optimization here. So we want to vary the different matrices plus BH and BV in order to minimize some cost function. And for example, in the standard case of maximum likelihood estimation, we want to actually maximize this expression, so the sum over the different log of PDXI, where xi are some sample from the real probability distribution that we are trying to estimate. And actually, the important thing is that since we have an analytical expression for this probability distribution, we are actually able to use both gradients and non-gradients based technique in order to find the solution to this optimization problem here. So these are a few example where we are trying to estimate different PDF. So we can see in blue, which is the real distribution that we are trying to estimate, and in red we have the output from the Riemann theta Boltzmann machine, and the histogram is a sample from the real distribution that we are trying to understand. And as you can see from this figure here, I mean, this approach is working both for the one-dimensional case and the two-dimensional case. So another interesting property about the Riemann theta Boltzmann machine is the fact that we are also able to sample this PDF PV. And actually, we can do this by using these laws of the total probability. So we can express PV as a sum over H over this conditional probability PVH times PH. And actually, the important thing is that the PVH is a multivariate Gaussian. And so we can easily sample this model by first sampling H from PH, and actually in order to do this we need to use the fact that we can evaluate this PH using the numerical evaluation of the Riemann theta function, and in particular it can be shown that if we fix a value of the ellipsoid radius r, which is actually the points over the integer lattice where we are summing over some appropriate radius r, we can actually find that the probability of finding a point outside this ellipsoid will go to 0, and actually we can recover that the sum over the different point h we are in this ellipsoid would be roughly 1. So using this first step, we are able to sample h from pH, and the next step is quite trivial. So it is just to sample V using this conditional probability PVH, which is just a multivariate Gaussian. So here are a few examples of the sampling. These plots are similar as before, but in this case, the histogram are the sample from our model and not from the real model. And as we can see, again, everything is working both in the one-dimensional case with this non-trivial probability distribution, and also in the multidimensional case. So the final property that I wanted to talk about is the fact that actually this model, the RTBM, behaves in a very interesting way when we apply an affine transformation. So if we change from a space, from the space of the vector V to this new space, which is actually described by A times V plus B, where H is a matrix which is a full column rank, we found that the new probability of the vector W will have exactly the same form of the initial probability PV, but actually the connection matrices and all the other values will just change according to this transformation here, where this particular matrix A plus is defined as the left pseudo inverse of matrix A. And here I show you in practice how this can work. So we have this RTBM in red, which is first trained to estimate this multivariate Gaussian function. And then we are simply applying a rotation of 45 degrees and a scaling factor of 1/2. And this could be actually very useful because there are a lot of affine transformation that are quite useful in machine learning, for example, a PCA. So the idea is that you can, for example, move to a new space where the training will be simpler to do, and then you can just retrieve your result by moving to the original space, and then you can simply apply this transformation law here in order to obtain the RTBM model, which is already trained in the initial space V. So this is what was done before, but this model has a few limitation, and in particular the fact that the learning process can be quite slow if we increase the number of hidden layers, of hidden nodes, sorry. And so if we are not able to fully use a large number of hidden nodes, it will be complicated to estimate, for example, some probability distribution, which are complicated in a low dimension, so some non-trivial probability distribution. But also, if we wanted to push this model to higher dimension, this will be pretty difficult, because we expect that in order to have some model which works quite well, we need that the number of hidden nodes must be at least, if not higher than the number of dimension that we are trying to fit. And why this happens, so why we have this problem that the learning processes can become slow. The problem is inside the Riemann theta function, and which has this mathematical expression here. So theoretically, in order to compute this, we are expecting to perform a sum over this integer lattice Zn. And of course, you can imagine that from a computational point of view, this will be incredibly challenging if we increase the dimension n. And actually, the computational times increase exponentially with the number of hidden nodes. So my task for this project was to find a way to improve this model and to overcome this problem that we are not able to fully train using a large number of hidden nodes. And in order to do so, I observe that actually there is a specific case in which we can compute an n-dimensional theta function just by using one-dimensional Riemann theta function under the particular assumption that our matrix here will be diagonal, so only diagonal entries. And in this case, we get this nice property here, where we can see that the Riemann theta function factorizes into this product of one-dimensional Riemann theta function. And this is actually what we want, because as I show you in this plot here, the difference in the computational times when computing a standard Riemann theta function, assuming that omega is still diagonal. So if you are not using this equation, we get an average time, which is exponentially increasing, as I already told you. But instead, if we are just computing one-dimensional Riemann theta function, we find that the times is essentially the same, since at the end we are still computing one-dimensional Riemann theta function, this one-dimensional Riemann theta function different times. And actually, but the problem is that can we actually do so with the probability expression that we have here? And here we need to compute two different Riemann theta functions. So this at the numerator here and this at the denominator. And actually, for the first term, it is quite easy to have a Q diagonal, since this is a input, if you want, of the model. So we can start directly by assuming that our Q is directly a diagonal matrix. But instead, for this second term, we see that it is quite difficult to impose a condition to make this matrix diagonal at the same time having also this matrix diagonal. I mean, this could be possible for future work. And but the important thing that we need to observe here is the fact that actually this term here is just a normalizing term, because it does not involve the state vector V. Therefore, the idea would be to change the cost function and just use a particular cost function which does not require that we have all these normalizing terms, because once we can get rid of this term, we can actually compute everything just using this theta function here, and we can simply impose that Q is diagonal. So everything will be linked to the calculation of one-dimensional Riemann theta functions. And this is where score matching comes into play. So score matching is this particular parameter learning methodology, which is based on the Fisher divergence, which is actually not quite well known. I mean, usually everyone is using the Kullback-Leibler divergency or other divergency, but in this case, we can see that here we have this square difference between the normalized gradients, and since we are dealing with the normalized gradients, we can already see how all these normalizing terms will cancel, because we have this probability at the denominator here. And now I will show you a few ways to simplify the previous expression, which was quite complicated. And actually, under the assumption that our model is sufficiently regular, and which is the case for the Riemann-Theta Boltzmann machine, since we have this exponential damping factor, we can have this nice expression here, which will depend on the gradients of the log of our probability distribution, and 2 times the Hessian of the log of the probability distribution again. And now I will show you how we can compute everything just by using the one-dimensional Riemann theta function. So it is quite easy to find this expression. So the the derivative of the log of p with respect to vi is actually this sum of terms, and the second derivatives can be computed quite easily in the same way. And this d and this h here are actually the normalized gradient and the normalized Hessian. And as I already said, if Q is diagonal, we can bring everything to just one-dimensional Riemann theta function. So we will have now that the complexity when evaluating the cost function will increase simply linearly with NH, with the number of hidden nodes, and no longer exponentially with the number of hidden nodes. And once we were able to do this, we decided to test this new model, trying to estimate some empirical PDF. And for example, we tried to test this uranium dataset, which is quite known in quantum, in machine learning. And we can actually see that if we increase the number of hidden layer, we can usually find a better approximation of the density estimation, and we'll actually compare the performance of our model with some state-of-the-art model, for example, with the normalizing flow and Cantor density estimation. We computed the Kolmogorov-Smirnov test in 2 dimensions in order to evaluate the performance of our model. And as we can see, in this particular case, we find that actually the lower values, we get the lower values by using the Riemann-Theta Boltzmann machine compared to the normalizing flow or the kernel density estimation. Then we decided to test with the other set. For example, this is the well-known faithful data set, where we have the number of eruption and the waiting times between the eruption, and finally also with the iris set here, which is also already well known. But the problem with this particular model is that they have a few number of points. So we can see that essentially every model struggle when estimating this density due to the fact that we have a low number of points. And actually we see that for this particular cases, the RTBM is not working as well as we thought, but we think that we can fix some of this problem by changing how our optimization work, because we are actually using CMA now, so which is a genetic optimizer, and we think that maybe if we try to use something more competitive, we can actually try to find a way to lower these values here. But we can see that we are nevertheless still competitive with some state-of-the-art models. So to summarize, I've told you about this new version of the Riemann-Theta Boltzmann machine, which we call the restricted Riemann-Theta Boltzmann machine, and I hope that I've shown you that this is a valid model to perform density estimation. And finally, I would also like to put an accent on score matching, which is actually a very underrated cost function, which in our case was pretty useful because it makes us able to train efficiently model using large values of the number of hidden nodes. Everything is open source and will be soon available here. And our plans for the future in order to progress with this particular model is to find a way to speed up even more the computation of the Riemann theta function, for example, by going through a GPU using GPUs and also FPGA, for example. And finally, since we have this very cool model for density estimation, since I have a background in high energy physics, it will be also useful to find a way to fit this in some Monte Carlo multidimensional integrations. So, for example, all the part of the importance sampling where we are trying to estimate which probability distribution we are trying to solve will actually be done by the Riemann-Theta Boltzmann machine compared to other standard model like Vegas or Vegas Plus. I think that this is it for me.
Thank you for the very nice talk. Question, or you want to take a mic? No, he was first.
It was a very, very interesting talk. Can you go back two slides? Okay.
This
here.
one?
Yeah. I mean, if I understand correctly, like you're performing well with a less number of hidden neurons, right?
Yes.
But don't you think that this might be a problem of the optimization procedure more than?
Yes, I think that this is sorry. Okay, that this is mainly due to the fact that this is just an average value, but we found that for some specific if we let the training go, in some cases we are actually able to find values which are much lower than the value that we have here, also for high dimensions. So I think that the problem is that we need to find a better way to learn and fine-tune this model, because actually all the ingredients are there in order to find a very good model for density estimation.
Thank you for your talk. And so it's more like a curiosity. So is there a particular, so as far as I understand, you're using a zero-order strategy for the optimization, no? Is there a particular reason for that? Why you're not using like some gradient first order method, like gradient descent?
Sorry, can you repeat the question?
Is there a particular reason why you chose to rely on zero-order methods for the optimization rather than first order, for instance?
Yeah. Actually, you mean why we are going to just one-dimensional Riemann-Theta function instead of?
No, you said that you're using genetic algorithm.
Yes.
So
yes.
why did you choose genetic algorithm?
Yeah, I mean, this is the algorithm that we have started with. So the previous version of the Riemann-Theta Boltzmann machine, which doesn't have all this feature of going to only to one dimension, was already using this type of genetic Hull algorithms, and this was very slow. So the first step in order to solve this was to try and use these tricks to go to just one-dimensional Riemann-Theta function. But at this point, we pretty much know that we will need to change this in order to find better results.
So I guess I'm not familiar with this Iris and Old Faithful. What are the dimensionality of those?
Where here?
Yeah.
This is the Kolmogorov-Smirnov test.
No, the dimensionality of these data sets, Iris and Old Faithful.
Yes, and this is actually all the tests that I've done here is for 2 dimensions. So you can see here that everything is just as an x-axis and a y-axis, and we are just trying to increase the number of hidden nodes.
You have not tried higher dimensions at all?
Yeah, the problem with that is that we wanted to try, but actually we couldn't find some test in order to.
But the standard UCI data sets like power, gas.
Yes,
but
the issue with that is that we couldn't find a way to quantize the performance of the model, because actually there are quite a few codes that make able to perform a Kolmogorov-Smirnov test. Or
but the standard way of comparing these results is not with KS test, it's with log P, right? You know, you just whichever maximizes the log density is the best.
Yes. So
why are you doing KS?
Yeah, I mean, we are doing KS because at the same time we also wanted to test if the sampling was still working for this particular model. But actually, you are right. Another possible estimator will be, in our particular case, just to minimize the Fisher cost function and not the maximum likelihood.
Okay, but you could do
Because we are doing the training with the Fisher cost
cross
function.
entropy as well. Right?
Yes.
But okay, so then I guess the other question I had, usually at least on those tests, first of all, there's 20 different normalizing flows, right? So I don't know which one you're using here. And second, normalizing flows always beat KD, right? So the fact that here it's not, I would say, maybe you're not using the state-of-the-art normalizing flow.
Yeah, I think that the main problem, as I already said, is the fact that for this we have a very few number of points. And that's why I think that every model in this case is struggling in order to obtain lower values of the Kolmogorov-Smirnov test.
Okay. Maybe you shouldn't like worry too much answering, but do you have a feeling of why this should be better than normalizing flows? Maybe it's not essential before you should work it out and see how it works, and
yes.
so maybe it will become clear why it's better. But because so the optimization is still not a complex problem, you
yes.
have to do it with gradient descent.
Yes,
and so it's similar to normalizing flows.
Yes,
and
but
so,
I think that the most valuable selling point here is the fact that the number of parameters that we need to optimize is actually very slow, because we are not dealing with a complex neural network, but you just need to optimize the number of components that you have for the connection matrices and for pH and BV, which are the vector biases. So actually, since we are trying to solve an optimization problem in a lower dimension, we think that it is still very valuable that we are able to obtain this performance here, considering that at the end we are using a very simple model and not a complicated model.
But you're saying that then this simple model will perform as well as the complicated model implicitly.
Yeah.
So you're saying this model is more synthetic?
Yeah.
Because the parameters are more useful than the ones
yes.
in neural network.
Yes.
That's your feeling.
Yes.
Well, I just wanted to make a comment. I mean, score-based diffusive models are beating normalizing flows precisely because normalizing flows have this constraint that they need to be normalized, right? So if you train on score, which doesn't have normalization, actually, they do beat them, even on the estimation.
Yes. In fact, another interesting point, as I told you, is to use this new cost function, the Fisher cost function, because actually some different models can struggle with the fact that you need to normalize them. So actually, in this way, it would be pretty useful.
Correctly, actually what the end result is a mixture of Gaussian. The end result.
Yes, it's a mixture of Gaussian, which is modulated by the ratio of the Riemann theta function. Yes.
Okay. So thank you very much once again.